and welcome to this presentation on memory optimizations in machine learning. My name is Tejas. I am a senior engineer at Netflix. And today I'll try to give a brief teaser about how memory is used in AI and ML models, and specifically what techniques you can use to optimize it. This is what we'll cover today. We'll go over why memory optimizations matter, and we'll cover some basic optimization techniques. Quantization, pruning, and efficient mini-batch selection being the three that we'll consider. And finally, why hardware plays an important role into this. So before jumping into it, I'll explain what I do at Netflix. So you may know Netflix with the movies that you watch, the shows that you watch and hopefully like. And turns out it's easy here to kind of produce or create shows, but more difficult to transfer or stream those shows to people that will be delighted by watching that. And machine learning plays a very important role in helping us build a very personalized platform that can entertain and delight people. When you go onto Netflix, and it's many models that run in Netflix. For example, your entire page is customized just for you. What that means is what rows you see, what do you see within each row. There are several models that dictate that. Not only that, when you look at a movie, the image that you see is customized for your profile. So even if there is another home member who has their own profile, they will see the same movie with a different image, because they probably like sunshine more or like a particular actor more than you do. And that is where machine learning makes a very, very personalized experience possible. However, as the size of models is increasing, so is the pressure on memory. Typically, when you talk about machine learning or AI, the focus is on, hey, we don't have enough GPUs, let's buy GPUs, and it's running short everywhere. What we observed in Netflix is that our GPUs are almost 40 to 50% utilized only in terms of compute. When you open a GPU, you not only see the compute side of GPU, but also the memory part. The memory is the one that actually gets the data inside the GPU for the compute to work on it. And this memory is typically HBM memory, which is high bandwidth memory. So you need to pump in the data fast enough to keep the GPU busy. And if your machine learning models or AI models are taking up a lot of that memory, that leaves a very little room for data to come in. And so some of these optimization techniques help to circumvent that problem. Let's talk about how the footprint in ML is growing. As you can see, machine learning and AI especially is now revolutionizing almost all the fields like healthcare, finance, e-commerce. Every other day we see a new model being deployed. Trillions of parameters, billions of parameters, some making videos out of text and so on and so forth. Models are growing in complexity. As you can see in this graph, and this is a very outdated one actually, it's even worse now. So you can see that the transformer sizes, and transformer is a type of architecture that is very famous nowadays, but it's growing at 400x every 2 years. Whereas the amount of memory that is available on the GPU chip is only growing at 2x. Which means at some point, you will not have enough memory in a GPU or a cluster of GPUs to support a model or to host a model. And therefore, you need to actually partition the model and have multiple GPUs, buy more GPUs so that the model can live in memory. And therefore, optimizations are needed for memory. They enable training larger models with lesser resources, deploying models on resource-constrained devices. This is especially true if you look at the future of AI. AI will be decentralized. It will be inherently private. You will imagine a future where you can have a lot of these AI models running on devices. And Apple Intelligence is already in a direction to do that. There is also federated learning and stuff that's going on. Beyond all of this is also reducing infrastructure costs and energy consumption by optimizing memory. However, there are challenges in doing this. You have to balance how much you can squeeze the memory out with how much performance loss you're taking. Also, there are diverse hardware platforms and architectures for which it may not be that trivial to optimize memory. Now, this is what typically happens in the AI lifecycle. You have a model that a company comes up with. And as the model scales, you also have optimizations, which means you release a smaller variant of the same model. This is true ever since GPT-3, 3.5, and Turbo came. It has stayed the same with GPT-4. And this slide is older, but it had GPT-5, but there's also this GPT-01 now that we all are familiar with. This is to say that along with releasing a big model, there are always these smaller variants out there. And therefore, the future would only have a lot of smaller models and very few companies working on really gigantic models. Before we dive into what we can do with memory, first let's understand why is memory even needed? Like, what does memory even hold in an AI model? So machine learning models consist of data structures like tensors and matrices, and this is like a 101. Tensors you can think of as a multi-dimensional storage of data. So if you have rank 0 tensors, it's a scalar. Rank 1 tensors are vectors. Matrices are rank 2 tensors, and you can have rank 3 or higher tensors as well. And the way memory is used is that if you have tensors that have a shape, a two-dimensional tensor of shape 1000 by 1000, which means it has 30, and each number is represented by 32 bits, which is typical in ML models, then you are using 4 MB of memory right there. And when you train a machine learning model, you actually store the model parameters, the gradients, and the optimizer states in memory. You also store the intermediate activations and backpropagation buffers. This is nothing but when you're training a machine learning model, you have a lot of data. You break the data into pieces, and each piece is then sent through multiple layers of the model, the neural network, or the transformer architecture. And every layer then starts with some random float numbers and adjusts their numbers so that the error loss at the end is the least. Once you get the error loss at the end, you backpropagate, which is you tell every previous layer, hey, can you reduce your error by some degree? And you so on and so forth, you propagate that through every layer. All of that information is stored in memory, which makes training faster. Imagine if you had to store all of it on storage and then read it every single time, you would never finish training. Not only that, like there's memory allocation and deallocation during forward and backward passes, and it is dynamic in nature. So there is a lot of potential for memory leaks and fragmentation. There are a lot of factors that impact the amount of memory that a model uses. Model architecture depth and width is a very important factor. Typically, the wider your model is, the more knowledge it has. But the deeper your model is, the more in a particular vertical, the deeper its knowledge is. So if you want a model that wants to do a bunch of things, you would just like have a wider model. But if you want a model to do one thing very well, you would go for more layers of depth. That's typically the rule of thumb. And depending on how wide or deep your model is, you will have a different amount of memory being used. The other one is the batch size. Like I said, when you have to train a machine learning model and you have terabytes of data, you want to chunk up that terabytes of data into smaller pieces. For each piece, you want to train the model, because the piece that you're sending in also has to reside in memory. So as we'll cover in the next few slides, but imagine if you have larger pieces. What does that mean? It means you will train faster, but it also means, or rather you will converge faster, but it also means it will take up more memory. If you have smaller pieces, it'll take some while, but it'll keep it within the memory bounds. Not only that, a larger piece may actually cover more variance than a smaller piece does in one particular training set. So there are pros and cons with every approach. But there are many advantages of compressing models beyond just the fact that it can save money. You can apply techniques like pruning and quantization that can reduce your ML model size by 75%, which makes it possible to deploy them on edge. There's faster inference, and this is the interesting part. As you compress models, the time it takes to get inference out of a model is also reduced significantly. So mixed precision and quantization can actually lead to 30 to 40% improvement in inference speed, enabling real-time applications on mobile devices. Imagine a future where you are running a huge model and for inference, you have to run it on GPUs. But if you compress the model, you can potentially try to move inference to CPUs just because its speed will be comparable to that of GPUs. This is an extreme example, but it's a good North Star to aim for. Lower energy consumptions because there are fewer computations and they reduce the power consumption by up to 4 times, which is very crucial for mobile and IoT applications. And deployment in resource-constrained environments. Like I said, AI on the edge or private AI, cameras and mobile phones without needing cloud resources may be very suitable for the applications of the future. Here is a snapshot of the different techniques and this list is growing. There's a lot of active research in this direction and you can see here that there are different types of hardware, different types of libraries and also different techniques that you can experiment with. There was a paper recently by Apple and someone interviewed a lot of Apple researchers, ML researchers, and asked them, what's your pain point with machine learning research or in general, like building models? And they're like, it's a black box. When it works, we don't know why it works. When it doesn't work, we don't know why it doesn't work, especially after optimization. So this is to say that even for the same model, if you deploy a quantized, optimized version of the model on different types of Apple phones, you cannot know how it's performing. And which makes this problem interesting because it's very iterative in nature. You try out some combinations, it's not great, let's try something else. And that's why there is a need for tools that can automate a lot of these pieces. Let's begin with the first one, data quantization. In very simple terms, all your machine learning parameters are represented by 32-bit float numbers. We want to convert those float numbers into smaller representations. How small can you go? You can go to 1 bit actually. There was recently a paper by Meta, or I think it was by Meta, that talked about you can go as low as 1 bit, which effectively means it's a 0 or a 1. And you can represent a lot of parameters by that. How good that is, how great that is, it's interesting. That paper has a lot of details. But effectively, if you can represent each parameter by a smaller amount of memory, then you've halved the memory if you go from float 32 to float 16. There's also B float 16, which is a variant of float 16, in which the mantissa part is smaller than the float 16 one. If you want to go to CPU instead of GPU for inference, then you would rather convert the float 32 to int 8, because that's what mostly CPUs will work with. There are benefits of quantization. It reduces the memory footprint by 50 to 75%, and there's a lot of faster computation and inference times. This captures the types of quantization pretty well. So there are effectively, there are 2 dimensions in which quantizations are different. One is uniform quantization. Let's say you have a space of float numbers. You will just divide it into partitions, and wherever the number falls, you'll just assign it a particular integer that represents that partition. This is uniform quantization. You've uniformly partitioned the space of floats from negative number, or let's say we only take positive, then from 0.00 to like whatever number that may be. But real world is not like that. In the real world, you have a lot of parameters that are very close to each other. And so you want non-uniform quantization, which is you don't uniformly divide the space, but as you can see here in this particular example, a lot of concentration, like the bell curve, is in the middle. So you would want more integer numbers to represent this space where most floats fall. So this is the non-uniform quantization. It has variable sized intervals. Then there is another aspect of quantization, which is, do you quantize a machine learning model after it has been trained? So once the model is trained, its parameters are decided. That's when you quantize it, or should you be aware of the quantization while training the model itself? There are pros and cons to each approach. Let's say your training job takes weeks to finish. You don't want to restart it by looking at quantization aware training, which is at every stage you quantize it. Instead, you would take the final output, quantize it, which is you do post-training quantization, and then see what is the accuracy loss you have. Whereas the other one is quantization aware training, in which while you're training it itself, when your model has to decide the value, it'll actually choose the value that is closer to the to whatever is the interval that you've decided. Quantization aware training is actually more accurate than the post-training quantization. However, for most practical purposes, what folks do is they quantize a model after it has been trained on, and then they use fine tuning with some samples to make up for the accuracy loss. So here are the steps for quantization. Let's say you decide to quantize a model, and you use post-training quantization. If it gives you good accuracy, then you just stick with it. If not, you go back and check if you have data set or not. And if you have your data set and your training resources, you use quantization aware training. And at that time, you need to, if you still do not get good accuracy after quantization aware training, you use fine tuning to make up for the accuracy loss. Now, this is a simple notebook that I wrote for explaining both of them. It's a PyTorch like framework, and we used BERT model, which is not that big. It's like less than 500 megs in size. But if you look on the left, I'm glad it's working fine. So here you can see that on the left-hand side, we have post-training quantization. It's as simple as like that one line of code that we added, which is you have a quantized model. And in this case, I wanted to quantize it to 8-bit. It was float 32. I wanted to bring it down to 8 bits. And on the right-hand side, it is quantization aware training, where we are actually training the model for, in this case, it's 3 epochs, but like we want to be aware of the quantization levels while training the model itself. And here are the results. If you see here, this is the size of the original model, and on the right is the size of the quantized model. And you can see that the accuracy has stayed exactly the same. The inference latency is actually reduced. So this means that by reducing the size, you've actually made it faster, kept the same level of accuracy, which is generally not true in real world. BERT is an interesting example because it's intentionally made filled with a lot of zeros and filled with a lot of float numbers for which just the before the decimal point is good enough for training. So this was an interesting experiment for quantization. Let's talk about the next technique. It's model pruning. In simple terms, you have a network of wires connected to each other, and you pluck out one wire after the other to make sure that whenever you pluck it, the two sides are still connected, which means that there is some wire connecting both the sides. And that's what pruning does. It removes unnecessary or redundant model parameters. In every layer in machine learning model, you will have a bunch of numbers, a bunch of values and vectors and parameters. And some of them will not be activated at all. They are just there, but like no inference job, or most of the inference doesn't even require that. That pruning's aim is to remove that. And there are a very, very basic thing that you can think of is, hey, you know what, if everything has a number, let's remove the ones that are closer to 0. And that's what the simplest pruning algorithm does. It is magnitude-based pruning, where you remove weights that have small absolute weights. But it's very random because you have to go over every layer, figure out which weights in that layer are closer to 0 and remove them. So you'll be left with a matrix that has a bunch of zeros spread out everywhere. That doesn't help you much if you want to do matrix multiplication. Sure, some operations will complete faster, but it doesn't reduce the memory. The compute is faster. That's all that it does. So instead, what you would rather want to do is remove layers altogether from pruning, and that technique is harder. It is structured pruning. So you need to be aware, like for a given model, which layers get activated and which layers are the ones that have the most zeros, let's say, and remove those layers altogether. Now that means you've completely avoided some matrix multiplications, and potentially, if your hardware supports it as well, you can have memory optimizations there. The goal is not just to save memory. The goal is also to save energy, and pruning is actually falls under the second category, where it saves energy by reducing computations. And then there is the process of you remove the least important neurons, and then you prune. This is pruning, and then you run your check the accuracy. If there's a lot of accuracy loss, you have a set of data that you've partitioned probably or kept it separately. You will use that to fine tune your pruned model. This way you can make up for the accuracy loss. No matter what technique you use, you will always have an accuracy loss because you have to give away something to get something. And our goal is to not have that as much as we can. So fine tuning almost always will help you whenever you have accuracy loss in all of these techniques. And like quantization, pruning also has a lot of benefits. It can reduce the memory footprint by up to 90% in some cases. And it also leads to faster inference times and energy efficiency. So this is an example of unstructured and structured pruning. Again, on the same sort of model. On the left-hand side, you have unstructured pruning, where what you do is you look at the model and in this case, I just look at the linear layers of the model. And I want to prune out 70% of the weights in this case. It's very aggressive. But because this model has a lot of zeros, intentionally bloated model, it actually works fine. So I don't care about which layer or rather which neuron I am looking at. I just remove the weights that are closer to zero. That's all I do here. And then finally, I evaluate the model. On the right-hand side, it's the structured pruning, where in this case, what I do is I want to prune some rows, 30% of the rows in the linear layers. So this is where I use the structured pruning that from the PyTorch framework. It's like, as you can see, it's very simple. It's like 1 or 2 lines of code and you can experiment with it. And let's move on to this part. Like in this case, I believe this is for structured pruning that I took the samples from, because for unstructured, it led to a lot of accuracy loss. The original model had a size of 438, like earlier. The prune model had a lesser size. The accuracy did not actually increase. This is like it falls within the error range. So this is to say that we did not lose a lot of accuracy. But the inference was again improved. It went from 30 milliseconds in this particular case to 26 milliseconds. And finally, the last technique that we will try to discuss is the mini batch selection. Like I said, you have to divide your training data into smaller subsets, and you want the impact of the batch size on the memory usage. Excuse me. As we talked about earlier, if you have a larger batch size, you will converge faster. As you can see here on the right hand side, as the batch size is increased, the training time is lowered, which means your model is training faster. But consequently, your memory usage is higher as your batch sizes increase. And there are strategies that can be employed to make the models better. One of them is dynamic batch size adjustment. Mostly people use static batch size. You start with a batch size and you live with it. But if you are aware of the amount of memory usage, the amount of resources available on your training infrastructure, you can dynamically tweak the batch sizes so that you can extract the most from choosing these. The other one is gradient accumulation. It effectively means that you do not, when you're doing the back propagation, you do not persist each entry in memory. Instead, you do a rolling, like you roll over the entries, or you just keep a computational checksum or computational value, and then you accumulate it and write it once. So this can help with some memory usage. There are hardware considerations in choosing batch sizes because optimal sizes differ for CPUs and GPUs. So typically for large models, you would train on GPUs only. But if you have smaller models that you can benefit by training on CPUs, it'll take a long time, but it'll still work and it'll be cheaper. Memory hierarchy, bandwidth impact the batch size selection as well. So the best practices are you want to profile the memory usage for different batch sizes and experiment with different sizes and gradient accumulation settings. You also want to see whether you want to converge to training faster or you want to use more memory for that. Memory optimization techniques vary across hardware platforms. On CPUs, you can leverage cache hierarchy and data locality, and you can also use vectorization, which is single instruction, multiple data for parallel processing. Whereas on GPUs, like I said, you can utilize the HBM memory, and you want to develop algorithms that use coalesced memory access for efficient data retrieval. Most of the time in training is spent in copying the data from the CPU memory to the GPU memory, or vice versa. And the way, there are some techniques out there to circumvent this amount of copying. Every new version of the GPU that comes out from NVIDIA, what it does is it introduces a layer of abstraction. So earlier, there are threads in the GPU that did not share the memory. So the next version of the GPU allowed threads to share it. And then multiple threads were a part of the thread control block. So now you have multiple thread control blocks share the memory as well. So this is one way of reducing the amount of overhead of copying memory between threads in the GPU. For CPU to GPU, there is a concept called pinning, which is you pin the memory of the CPU and the GPU, and that prevents the back and forth, but it can only be done for some amount of memory. So that is to say that you want to minimize the data transfer between CPU and GPU, and there are other techniques, like there is in-memory compute, which is rather than, there's a very nice lecture online on this where you are not trying to bring the data to compute, but compute to data. A lot of the real estate on GPU or even in ML model training and inference is spent on how can we get data faster, closer to the compute. But in-memory compute is this new paradigm where your memory itself has compute in it, and you can get the compute closer to the data sources. There are also specialized accelerators like TPUs and FPGAs that leverage a lot of on-chip memory for fast access, and they optimize the data flow and computation graphs. These are specifically built for matrix multiplications and other types of operations that are very common in ML. Here are some real-world examples of how all of these techniques that I talked about have changed, or companies have used them. MobileNet is deployed on Google Pixel, and it uses pruning and depth-wise separable convolutions to reduce the memory by 75%, and it improves the inference speed by 30 to 40%. BERT, which is a model that we use for our experimentation, pruning 50 to 80% cuts the memory usage by 30 to 40%, and without accuracy loss actually, and it enables real-time translation. Xalient's Edge AI. So Xalient uses facial recognition models in smart cameras, and it reduced the memory usage by using these techniques, and it allowed for real-time video processing, eliminating dependency on cloud. Similarly, you see Facebook's PyTorch mobile. Pruned and quantized models are deployed on mobile devices, and they enable real-time AR/VR applications on phones. Now, this was an experiment that I was running, and like I said, one of the challenges with ML and AI is the fact that you cannot, you have to try multiple things. You have to try quantization, pruning, see how much accuracy loss is there, etc., etc. In this particular experiment, we try all of them. We programmatically try all of them. In this case, our goal was to reduce the latency. So this is the original model. These are the metrics for the original model. And here you will see that we converted it into the ONNX format, which is a format for ML models. We use different types of transformation techniques. We use pruning, quantization, and we tried multiple. It's like hyperparameter optimization, which is nothing but you have thousands of knobs and you tweak each one differently and see the result and pick the one that has the best result. In this case, we tried 2 or 3 combinations, and we saw that this particular combination gave us the best latency. As you can see here, the latency went from 34.16 to 31.52. The accuracy though, this is a more real world example. So the accuracy, which was 86% on average, actually became 83.33%, which is expected because for this much loss in accuracy, we gained in the latency, or rather reduced the latency. There is a middle ground here where you see that the minimum latency, or rather the accuracy loss is still there, but some metrics are better than the original model. However, overall, we picked the model in the middle because this is the one that had the best latency, accuracy, and it was within our accuracy loss of 3% in this case. So this is to summarize the different techniques. You have pruning, quantization, and the ones that I did not cover are knowledge distillation. Pruning itself has unstructured pruning and structured pruning. The quantization has quantization-aware training and post-training quantization. And knowledge distillation, which is an entire big topic in itself, is effectively the idea that you have a huge model. In simple words, you constantly ask this huge model some questions, and based on the answers, you train a smaller model. And this means that your smaller model has some amount of information that a huge model has. And I'm very simplifying it a lot here, but that's typically used by these OpenAI and Claude and others to actually bring out smaller models. So these are avenues for future research. Ideally, there's a lot of focus on neural architecture search for memory-efficient models. It's effectively choosing an automated search for optimal architectures that balance performance and memory usage. This means that, let's say your goal is to find people in a shopping mall, hypothetically. You just come up with that goal, and neural architecture search will find the best model, how many layers, how wide the model should be, to satisfy that task. So you don't need to throw a huge model at every problem. Quantization-aware training is another area of research where we already have the basics there, but there is a lot of value in jointly optimizing parameters and quantization parameters. How can we extend that further? The third one is sparse representations and computation. If you prune models, you will tweak a lot of the parameters to be closer to zero or make them zero. So that means your matrices will be will be sparse. Some platforms support sparse matrix multiplications faster than other platforms. So a lot of research is in how can that be made faster on existing ones or the ones that don't really have it yet. There are other like hardware, software co-design and memory efficient transfer learning, where you can use adapt large-scale pre-trained models to resource constrained environments, which is via knowledge distillation and other things. That's my time. Thank you so much for joining me. And I open the floor for any questions. Yes.
So my question is that in previous talks, everyone's saying like go bigger models, everything's getting bigger, and then you're going the opposite direction. And is it because Netflix doesn't see value in going larger, or are you trying to quantize to get more data? Like, how do you see where you fit in this AI and ML revolution?
Yes. So the question is that a lot of talks focused on making models bigger, larger, but this talk focused on making models smaller. What does it mean for Netflix? Where does Netflix fit into this picture? And is there value in a larger model or a smaller model for Netflix per se? I would say that Netflix, this is my personal opinion, we power recommendations. Recommendations are a machine learning problem, typically, not an AI problem. And so most of our models are very small already. And however, as generative AI is coming up, there will be a future where the sizes of models will increase, inevitably. And therefore, we believe that just machine learning is enough for Netflix for now. To the larger question of, are larger models better? Why are we trying to go for smaller models, or which one is better? Yes, larger models are better in general. They can keep a lot of knowledge in them. But do you need one large model, or can you have multiple smaller models tackle the same problem? This is what some concepts like mixture of experts and others do, where you have a huge model, but only parts of the model get activated when you ask a particular question. So instead of having such a huge model, why don't you have smaller parts and have a good intelligent routing layer that can take the query and route it to the appropriate smaller model to answer to the same degree? Like I said, the wider your model is, it has more information about the world. But the deeper your model is, it has very, very deep specific information. So instead of building a larger model that's wider, you can imagine a future where you have a lot of deeper, smaller models. The advantage is twofold. One is that, it's easier in terms of energy efficiency. It possibly is easier to make AI decentralized. But yes, it is a core distributed systems problem where you now, and we've seen this revolution so many times, you now have to manage the communication between these models. You have to manage the security of the communication. So you look at ways in which you encrypt the data when you're communicating with parameters across these models. How do you do distributed training? How do you do distributed inference? These are interesting questions that research is looking at. But I believe that inherently that is where AI will shine. We will not need one model to rule them all if you're a Lord of the Rings fan, but we will potentially have a lot of models in the world out there, and each one will be for very specific tasks. That's how I think.
Thanks.
Yeah. Any other questions? Going once? Going twice? Thank you, everybody.